Okay, this is a video on section 6.4, enthalpy of chemical reactions. We're going to break this up into 2 or possibly 3 videos depending upon how much material there is. And so let's get started. Well, as you know from the first law of thermodynamics, delta U is equal to Q plus W. So this is the first law of thermodynamics, and it basically says that energy is neither created nor destroyed, just transferred from one form to another. And that is true since the change in the internal energy of a system is equal to the amount of work done on or by the system, and or in summation with the amount of energy released in the form of thermal energy, in other words heat, and that is the heat transfer occurring from the system to the surroundings and from the surroundings to the system. Okay, so as you know, W can be replaced with P delta V, and that changes it to negative, assuming that work is done by the system. So it comes out to be minus P delta V, or Q minus P delta V. What if delta V is equal to 0? In other words, what if we have a constant volume situation? Then we know that delta U now becomes equal to Q sub V, where Q is the heat and V stands for constant volume. So under constant volume conditions, we know that U is, or delta U is equal to the amount of heat under the constant volume conditions. Now, constant volume conditions are often kind of difficult to maintain, and so not a lot of things are done under constant volume conditions, but most things that we do in terms of chemistry can be done, are usually done, and are done under constant pressure conditions. So what happens, let's try that again. What happens to this equation when a reaction occurs under constant pressure conditions? Well, let's take a look at these equations again. Okay, so delta U, as you know, is equal to Q plus W. All right, now if we keep the pressure constant, right, constant pressure conditions, Q becomes equal to Q sub P. We take this equation, we rearrange it a little bit, and Q sub P becomes equal to delta U plus W. Okay, let's say, no, it's not plus W. Shouldn't it be minus W? And it should, so it's minus W. And if we, of course, if we replace W with minus P delta V, Q sub P, that's a terrible looking Q. Q sub P becomes equal to delta U plus P delta V. So, under constant pressure conditions, Q sub P is equal to delta U plus P delta V. Now, we're going to introduce to you a new, not new, but new to you, thermodynamic function, which is called enthalpy. Enthalpy. Enthalpy is given the symbol H. Now, we're not going to do a very good job of defining what an enthalpy is, okay? It's not a well-defined thing. It is a thermodynamic function. It is significant, and we're going to show you how it is significant in a minute. Let me get rid of some of this stuff here. It turns out that enthalpy, H, is equal to U plus PV. So therefore, my friends, if this is the case, which it is, delta H must equal to delta U plus P delta V. Now remember, P does not have the delta in front of it because this is under constant pressure conditions. Well, didn't we write down this fact earlier that Q sub P was equal to delta U plus P delta V? Look, my friends, this equation, check, and this equation, check, look very, very similar. In fact, they look pretty much the same. Therefore, this thing called enthalpy, delta H, is equal to Q sub P. This delta H thing, this enthalpy change, or the change in the enthalpy, is equal to the amount of heat released or absorbed by a system under constant pressure conditions. So, why is this important? Why is this significant? And why use enthalpy at all? Well, one of the reasons is this. If we look at our original equation, which says that delta U is equal to Q plus W, we find that delta U is a state function. Yet it is determined in terms of two functions which are not state functions. These two things are not state functions. Neither heat nor work are state functions. Not a state function. So we've got these things defined in terms of things that are not state functions. We've got a state function determined or defined in terms of two things which are not. So we take care of one of these problems when we replace W with minus P delta V. Because P, whoops, I think that delta V, sorry about that. Because P is a state function and V is a state function. So since they're both a state function, work is now defined in terms of delta V. Enthalpy, and particularly enthalpy change, is also a state function. It's equal to H of the products minus H of the reactants. Now again, we haven't defined very well what an enthalpy is. And again, we're not really going to. We just know that it is a thermodynamic function. This is an R. It's a very ugly looking R. It's an R for a reaction or reactants. We know it is a thermodynamic function, and we found out earlier that the change in the enthalpy is equal to the amount of heat under the constant pressure conditions. So we see that delta H in reality is a state function because it only depends upon the enthalpy of the products and the enthalpy of the reactants. Enthalpy of the products, which is the final state, and the enthalpy of the reactants, which are the initial state. And so we take the difference of the two, we get delta H, and delta H we now know is equal to Q sub P. Therefore, in the end, my friends, we can now define the first law of thermodynamics as being equal to delta U is equal to delta H minus P delta V. Oh, I'm having trouble with my deltas today. Delta V. Okay, there's delta V. And now we have a state function that's now determined or defined in terms of two state functions. So remember, delta H, the change in the enthalpy, is really equal to the amount of heat either gained or lost by the system at constant pressure conditions. And we're good with it. We like it. It's a good thing. And with that, there we go. Oof, got rid of that. That was ugly. Okay, so this is pretty much what you need to know so far. And we're going to break it down into a second video, and then, last but not least, a third video. Okay? Enjoy.